Okay, so we start the class. So do you have any questions about midterm? Antarang, do you have a question? You said.
Well, yeah, I guess I was on for C. It says calculate AUC using five-fold cross-validation.
Sure. Yeah.
I don't really know, I guess, understand what the question's asking. So,
so AUC is just a error function. Okay, so AUC is similar to error rate or mean square error. So basically, we want to do cross validation. So we divide the data set into 5 subsets of equal size, and you run regression basically 5 times. In each time, you use the 4/5 of observations as training set and the other 1/5 as the test set. And you repeat that 5 times, then take the average AUC size. So that is what I'm asking that in that question.
Okay, so it's the delta from the cv.glm function.
I'm not expecting you to use some specific functions. You can just write the code to do cross-validation. If you find a function, that's fine. I personally don't know, but maybe there's some options in CVGLM or some other functions can do that. I'm not exactly sure, but I would rather write a code. It's not that complicated because just you have to run the same thing 5 times with different data sets.
Okay, got it.
Yeah, and also I got some questions about question 2a. The question 2a that I'm asking scatter plots, and one student asked me there was that should be pairwise plot or just the 6 plot, the one predictor versus the also. And I'm expecting pairwise scatter plot, even though it wasn't clear in the sentence. So 2a. Pairwise scatter plot you can generate at once by some specific function. Okay, so how many students here today? 6, maybe 1, 2, 3, 4, 5, 6, 7, 6, maybe 6. Yeah, so I want to do the exercise today, and maybe at first. Then after that, if we have more time, then we go to section 6.3. So yeah, so I open the file. So exercise 7 is about doing rich regression and the lasso regression. So let me see. Exercise 7, sorry, and the data sets are available on the website. And the 7 is using some data set about Apollon. This is a popular data set in UCI data repository. So this data set includes the 4,475 observations. I have already excluded some outliers. And our objective is to predict the number of rings that is about the age of those Apollons. And there are 9 predictors, the gender and the, maybe I would say the 8 predictors. And the gender, we have the 3 genders, the unidentified and the female and the male. So as a factor variable, we have the indicator for female and the indicator for male. And others are numeric, the length and the diameter, height and weight, and shucked weight and the visceral weight. I'm not exactly sure about the shucked weight and visceral weight, but some specific, the weight of some specific part of Apollons. Yeah, so sorry, the female, male, and the infant. Yeah, but the infant maybe I unidentified. And and we want to estimate a linear model. So simply we can fit y on x1 to x9, but we want to explore the more complicated situation. So we consider up to the three-way interaction. So that means we include predictors such as x4 times x5 or x1 times x6 times x8 or x7 cube. So those kind of variables. So product of up to any three predictors. So we have many combinations. So basically, we have the 9 choose 3. No, actually, we can choose the same thing. So the 9 cube, slightly less than 9 cube, right? So x1, x1, x, for example, maybe I would say x3, x3, x4, and x3, x4, x3 are the same. So they maybe slightly less than 9 to the third power. So maybe like the 600, 700, I don't know. So we include this. And so the original data set that is the Avalon one that is also available in the website. So that is this. Maybe this is a little too small. Yeah. So the indicator for the sex is equal to female and male, and length, diameter, height, weight, shaft weight, visceral weight, shell weight. Then rings. Rings is the response variable. And also I prepared another data set. This includes all interaction terms or square term, cubic terms. So x1 to x9 are the predictors, and I also put this kind of interaction x1 times x3. That's denoted as x1.3. Maybe later we have the three-way interactions. For example, x1, 3, 3, or something like that. X1 and X2 are just exclusive indicator variables because male and female. And also indicator variable square doesn't really matter. So I ignore X1, X1, X3. That is the same as X1 times X3. So only necessary the interaction terms, like X7 cube, for example, here. Yeah, so and in this case, we have many predictors. I think, I don't know how many, actually not that many, 191 predictors. So using this data set that we do some analysis. So first one, just simply the pairwise the plot to see the overall tendency between x1 to x9 and y. And then the regress y on the all three-way interactions by Lasso. Actually, this time the only Lasso, not ridge regression. So we have 197 predictors, maybe, and we have to optimize lambda. So determine optimal parameter lambda by cross validation. And after we find the best cross validate. Best lambda, then we decide the model and count the number of parameters, parameter estimates, which are equal to 0. So Lasso makes many parameters equal to 0. So out of 197, how many parameters are non-zero? And how many parameters are 0? Then also we compare this with usual the multiple linear regression that with only the first order terms. So just fit y on x1 to x9 and do backward deletion to drop unnecessary ones. Then calculate MSE for tenfold cross validation and compare the result with this Lasso model. So that's the question. Do you have any questions so far? Okay, otherwise I will split the group into 2, and maybe you can discuss this for maybe 10 to 15 minutes, maybe 12 minutes at first. Okay, so I will set up breakout rooms, 2 breakout rooms for 12 minutes. Yeah, okay, so Okay, go ahead.
Oh, Professor, you're muted.
At first, I will ask you which questions you finished. Okay, so far you finished maybe A and B. So at first, I want to explain something about how to create the variables in Avalon 3. Okay, so this is the my solutions. So we are using the GLMNet and the library boot for cross-validation. So GLMNet for Lasso. And okay, so this is not the question itself, but this is how I generated the data. So original data set is Avalon. So this is basically the same one as Avalon 1, but it includes some outliers. So 2 outliers with the variable height. So I excluded those variables. Then if you modify the data, you can use this write.table function to automatically generate the CSV file. You can specify whether or not you use the separation symbol and also row names and also column names. Yeah, so write.table function is convenient to modify the data set in R. And okay, so next we think about the interaction, and we want to use the name such as x.1, x1.2.4 or something like that. So I just prepare those names. So the x1 to x9, you can type x1, x2, x3, x4 and use quotation, but also you can use this paste function to automatically generate multiple names, x1 to x9. So paste x1 to 9, then you can generate it. Then, okay, so I make variable. So actually my code is not super general. So at first, 2-way interactions here. And after that, we make 3-way interactions. So 2-way interaction. So basically we have the 2 indices, I and j. So we multiply the i's column and the j's column to create the xij. So I name it as xi.j. So I and j are numbers. So I is equal to 1 to 9, and j is equal to basically the 3 to 9. Max 1, yeah. And of course, we don't have to create the x4, x3, right? So we only need to create x3 and x4. So just the increasing order only. So j is larger than or equal to I. And x1 and x2 are both gender variable. Those are exclusive to indicator variables. So we don't have to calculate x1, x2, or x1 square or x2 square. So x1, x3 is the first one. And we do this, and we add new columns to existing data set too. And in this way. So we define another column here and also another column name here. And remove the vector with zeros. What's this? D2 is the D2 -1. Yeah, I think that there is one redundant column, so we remove that. I don't know why we have this, but yeah. And the 3-way interactions that we can do the same way. They're using the loop for ijk. Then we can generate, for example, x4, x7, x9, or x3, x3, x8. We can generate those variables in this way. And again, write table. Then this is the scatter plot. You can see that maybe this is there are too many variables, but you can see there's some complicated relationship between variables. So length is the one-dimensional quantity, and the weight is three-dimensional quantity. So we have some, curvature if we make a scatter plot of length and height, length and weight, for example. Length and height, still it's not linear, but the length and weight, the more clear pattern. And also even the two weight, that we have some curvature here. And this is the ring. So the relationship between ring and other variables, it's not very clear. Maybe we need the transformation of variables, but for now we ignore it. Okay, so that's the how to generate it. And yeah, okay, so some of you have finished the B, so we do also B. So lasso regression, we can use the glmnet function. Alpha is equal to 1, and the what's that? Lambda value, you can differentiate it. So this is just one example of lasso with lambda is equal to 0.01. Based on lambda value, we have different result. Lambda is larger, more coefficients are 0. Even lambda is 0.01, many of them are 0. Only a few of them are non-zero. So these are coefficients. Okay. So next you can proceed to determine the optimal lambda. Then you can search for the best model. Maybe we will open the breakout rooms again. So do you have any questions so far? Okay, so I maybe shuffle the rooms. I don't know, delete, and okay, 2 rooms. And 1, 2, 3. Okay, so we start the room. How to do that? Yep. Okay, so 10 minutes more. Maybe 12 minutes. Yep.
I think you're muted, Professor.
Six, 7. Maybe one more. No. Oh yeah. Yeah. I think the many of you have difficulty to do the cross validation. There are several ways to do, but actually 2 of you have finished it. Finished at least C. So C determined the optimal tuning parameter for lasso. What was the optimal parameter? The 2 of you have done C. What was the value of lambda? Anyone? I think 2 of you have finished. So you got lambda or maybe log of lambda, right? Okay, maybe. Okay, so maybe I discuss how to do it. And C, there are several ways. The one way is to fit just a GLMNet function and use lasso and specify some several lambda parameters. And another way is to use the cv.glm function. So you can automatically choose the best lambda. And I used the cv.glmnet function. And this is data, so the predictors, and this is y, so response. And just you can do this, and you can get the entire result. So this is the result. So this is the log of lambda. So lambda is equal to 0. That means the log of lambda is equal to 0, means lambda is equal to 1. And -4, maybe about negative 50, 1 over 50 or something like that. And here maybe negative 100. Sorry, the 1 over 50 and 1 over 100, maybe around here, and so on. And you can see that this is the optimal point. Yeah, actually, it depends on how you run, but the about -7. Sometimes it's around -6, maybe -6 to -8. Before taking logarithm, the optimal one is this one. You can write the $ lambda.minimum, min, then you get the minimum one. So about 0.00056 here. Last time I ran, that was 0.0015, so maybe 2.5 times larger than this. Does anyone else get some answer for this best lambda? So anyway, so the result isn't super sensitive to the lambda value. So probably the value around 0.001, 1 over 1000 is the optimal lambda. Then what's the size of mean square error? Okay, so it has already been calculated in cv.glmnet function. So just we choose the index which gives the best lambda. Then we get the cv.lasso. So this is the cv.glmnet object. Then cvm index. Then we get the minimum, the cross-validated mean square error. That is about 4.439. Last time I ran 4.444. So that is probably around 4.44. That is the performance the lasso model can achieve.
Professor?
Yeah.
What was the minimum lambda you had gotten?
Lambda value, which gives the minimum MSE, is 0.0005.
Okay, yeah, I think I got that.
Okay, so it depends on your random number. So last time I got the 0.0015, so 0015. So probably it's 2.5 times larger than this, but you will get probably the value around that, right? If yeah, your answer may not be exactly this one, but okay, I see. I think another person got C. What value did you get? No others. Yep. And now that we count the number of zeros, so this is the estimated parameters. Okay, so we specify lambda is equal to b lam. This is 0.00056 in this case. And then we get these estimates. You can see that maybe roughly half of them are zeros and the other half are non-zeros. So yeah, this. So you can type the coefficient of this object to get this. So this part is not really necessary if we don't type this part, just coefficient LAS3B, it will give a matrix, 192 by 1 matrix. In this way, you can get some kind of list. And you can get the number of zeros as 73, number of non-zeros as 119. So slightly more non-zero parameters. Last time I ran, the lambda was 0.0015. It's larger, so it penalized it more. So this number was 60 rather than 119. And this number was 132 rather than 73. So yeah, it really depends on your random numbers. So, but roughly speaking, maybe half of them are zeros and the other half are non-zeros. Yeah, so it varies. Last time I got 60, but this time I have 119 non-zero parameters. But anyway, the performance does not change. So cross-validated MSE was anyway 4.44, around 4.44. And question G, I think this is also useful in the midterm exam, because I think one question asked the stepwise regression. Okay, so we do generalized linear model rings. This has to be GLM because not really. Yeah, LM we can also use. Yeah. If we want to use the cv.glm function, we have to use GLM. I think that later I use the cv.glm, so that's why I put this as GLM. Yeah, so we will use cv.glm. The result is the same even if you use LM, but the cv.glm function returns error if you use LM function. And this is full model. The dot means all variables except for rings. And the best model is the stepwise regression of LMF. And a trace 0 basically does not return any intermediate model results. Especially in the midterm, you want to limit the number of pages. So the trace 0 is useful command. Otherwise, you will see all intermediate models. Okay, so final best model is here. Rings on sex F, sex M, diameter, height, weight, shaft weight, visceral weight, and shell weight. So 1, 2, 3, 4, 5, 6, 7, 8. So I think that originally we have 9 variables. So we dropped one. What was dropped? Maybe length. Length was dropped, maybe. Yeah. Length has been dropped. So these are variables we keep, and all variables are very significant, you can see. And cross-validated MSE is 4.77. Last time I ran this, the result was 4.77. So probably that is pretty consistent. So about 4.77. 4.774 last time I got. this time 4.767. So around 4.77. So three-way interaction model by Lasso, that is 4.44. So at least it's better than this model. Yeah, so AIC has sometimes trouble when we have trouble to estimate the error size, the residual size, the sigma square, but the CV cross validation is pretty objective, the measure. So if we got 4.44 and the other model 4.77, certainly the model with 4.44 is better. Yeah, have any of you did any the data competition before, Kaggle or cross crowd analytics or any other? So usually when I haven't done the many data competitions before, but at first I run this kind of the base model, logistic regression with stepwise regression, or linear model with stepwise regression. And usually the performance of that model is the bottom 10%. So that means even this simple model that we can beat 10% of people. Maybe one reason is that some people write a wrong code to do data competition. So they output the nonsense prediction, then the performance is even worse than this kind of very basic models. And some others maybe even don't know stepwise regression, so it's worse. Yeah, about bottom 10%, that is my impression when we use stepwise regression. So we can do much better. And the three-way interactions with Lasso, it performs pretty well, even compared with the some more advanced models, such as support vector machines. Usually it's as good. Yeah, these days neural network is much better, some people claim, and the tree-based methods may be also better, depending on the question. Yeah, so this is the exercise 7. And today's homework, maybe I have already given the homework after the last lecture. That is similar to this, so you can use your knowledge learned in exercise to do. Maybe I have to upload this to the Canvas also. Any questions? Oh, sorry, I think oh, yeah. Yeah, so if you don't have questions, maybe we start, we go back to chapter 6 to go to the next section. The next section is also very interesting and includes important concepts. So I have 50 minutes, so so 6.3. So 6.3 is the dimension reduction technique. So suppose that we have many predictors. Then before fitting y on x1 to xp, we want to summarize the information of x1 to xp. Maybe simplest case is suppose that we have the variable, economic variable from each state, maybe production, industrial production for each state. Maybe we have, okay, so 50 series, so 50 variables. And okay, so we want to predict just the overall real estate price. Maybe that's a little bit hard. So maybe overall, maybe producer price index, for example, that is maybe closely related to industrial production. So then suddenly you want to summarize those data from 50 states into one, maybe overall average or total production of all states. So take average of x1 to xp or x1 to x50, or take a summation of x1 to xp. So that is the basic idea. So in general, if we have many variables, like the p is 100 or 1000. Then we want to summarize this data into very important, maybe 3 variables, maybe Z1 to Z3. So in general, Z1 to Zm. So M is usually much larger than, smaller than P. Then all of the Zm, Z sub M is the summation, linear combination of X1 to Xp. So that is certainly a good way to summarize the data. Then after that, we fit the data, Y on Z1 to Zm. Then we have much fewer variables, but the most important information are included in Z1 to Zm. For example, if we have the 50 variables from each state, the aggregated variable has basically most important information. So Z1 has the majority of important information to explain why. Yeah, of course, it reduces the computational burden. So if we fit Z1 to, if we fit Y on X1 to XP, that is the regression with 50 parameters, maybe including intercept 51 parameters. We have to calculate inverse matrix of 51 by 51 matrix if we do linear regression. So that is complicated, but if we summarize that variables into 3 variables, we only have to fit maybe 4-dimensional one. So we only have to calculate 4x4 inverse of 4x4 matrix. And the question is how to summarize the data. So if we have 50 variables, take average, that is easy. But in general, what's the best way? Sometimes just overall average is not good. We may need some weight. For example, we want to estimate the average graduation rate of Michigan universities. Then certainly we should put a larger weight on maybe U of M, Michigan State, and so on. And we should put a smaller weight on smaller colleges, such as maybe Henry Ford College, or, and so on. And sometimes some predictors are just the more important than other predictors. Yeah, so I don't know, the weight gain of animals by food intake, and maybe food intake of some specific vegetables don't really matter, but the food intake for like, I don't know, maybe the more fat, the materials including more fat indicates the more weight gain for animals. So for some variables, we put larger weight. So what's the best way to define Z1 to Zm? These are linear combinations, but what weight are the best? And then one popular way is this principal component analysis. So basically, we want to make the Z1 includes most information, and the Z2 includes most information except for Z1. Z3 includes most information except for Z1 and Z2, and so on. So that is the idea. So maybe it's good to see the figure. So suppose that we only have 2 variables. So this case, the P is equal to 2 and M is equal to 1. Then we have 2 variables, the population and advertisement spending. So this is from some data set. And if we are allowed to use only one predictor in the model, the one good way is to use the what should I say, the signed distance on the green line. So watch this. No, the signed distance. Maybe the signed coordinate. The coordinate on the green line. So we have this axis. This is a new axis, and we think about the coordinate on this axis. Say maybe we say this as maybe what, the Z1. So maybe here the center, so Z1 is 0, and this Z1 value maybe, I don't know, maybe 50 or something, and this Z1 value maybe the 24 or something, And this Z1 value is maybe -80 or something. So if we project all points onto this green line, then that includes the most information on this data set. So except for the signed coordinate, the coordinate on the Z1 axis, then we don't have much information. We have some variation, so the distance from each point to this green line, but that is relatively small. Most information is summarized as the coordinate on the Z1 axis. So in this case, that we should use the Z1 as this. Maybe to be accurate, that we think about at first the line perpendicular to Z. Yeah. Then we have the normal vector. So this is for Z1. So I would say this is N1 vector. So this is a pair of two numbers. So this is the phi, sorry, the phi1, yeah. Phi11 and maybe phi21. Phi12, just notation. So Zm is phi jm. So j is equal to 1 to p. So the coordinate j1, 2, so 1, 2, yes. The phi1, phi2, phi11 and phi21. And the Z1 is defined by phi11 times x1 and plus the phi21 times x2. So this is the way to choose the first principal component Z1. So here p is equal to 2 and m is equal to 1. So if we think about m is equal to 2, then we use the other direction. So that has basically the least information. So originally we have two variables, and after transformation, Z1 includes most important information and Z2 includes least important information. So that is the idea of principal component. So that means, yeah, so we minimize the sum of squared distance between each point and this green line. So such a green line gives the first principal component. And the first principal component usually has high correlation with any variables in the data set. So population and other spending. So basically we summarize those data into one variable. So that is Z1. So Z1 has high correlation with population and high correlation with ad spending. I would say in absolute value. In this case, both are positive. So sometimes that we have negative relationship, but that we have high correlation in absolute value. Sometimes they like this. So negative correlation is also possible. But most of the time, the majority of variables have high correlation with Z1. And Z2 is most irrelevant to the original data. So if we think about the second principal component, that has lower correlation with these two. In general, if we have the p variable, p is large, p variables, and the Z1, Z2, Z3, up to maybe Zm, the first several ones have high correlation with several variables. Suppose p is equal to 100. Usually the Z1 has high correlation with all of 100 variables. I mean, in absolute value. Z2 also has high correlation with the majority of variables. But the combination of the coefficients are slightly different. Maybe next one, summarizes the ideas. So the principal components may be and may not be interpreted in the context of the data. So for example, suppose we have the data for 1,000 students, test scores for 1,000 students, and we have 5 variables: the English score and the math score, science score, social studies score, and French score. Then when we do principal component analysis, typically the first component is like this. So just a kind of the aggregated variable, just the summation of these 5 or average of these variables. So usually we limit the set of these coefficients have the unit length. So the 0.45 square plus 0.45 square, the sum of the square of this is equal to 1. We do such a standardization. Anyway, if we multiply everything by 2, basically we have the same information, just the scale of the variable is different. So the first component is usually a kind of just the weighted average of those variables. So all coefficients are positive, or maybe sometimes all coefficients are negative. That doesn't matter. You can put all negative coefficients here also. But anyway, so that is usually the first component. And the second component, it really depends on the problem. But typically, the second component looks like this. So -5 times E, 0.5 times M, 0.5 times S, and 0 times SS, and the -0.5 times F. And this component may be the tendency towards scientific areas. That you can see that the math and science, we have positive numbers, and English and French, the negative numbers, and social studies, 0, so in between. So you can interpret this as maybe tendency towards scientific areas, but not always we have this kind of interpretation. So this is just a data-oriented method. So sometimes the second component, it's harder to interpret the coefficients. I think in most cases, maybe first component, second components are fine, but other than that, it's really hard to exactly interpret the idea. Yeah, maybe another example, I worked for a bank, so I used the principal component for interest rate. Interest rate depends on time, so each variable is time series. And the interest rate is actually, there are multiple interest rate depending on the maturity. So just 1 day interest rate, that is policy rate, and 1 month rate, or 3 months rate, 6 months rate, 1 year rate, 2 year rate, maybe 5 year rate, and so on. So we have many rates. Then how these interest rate moves. For example, currently 1 day rate is very small, like 0.25, 1 month, maybe 0.4, 3 months, 0.6, maybe 0.8, 1.1, 1.2, 1.5, or something like that. How these values change over time, and the most common movement is just parallel shift. So every interest rate goes up, or every interest rate goes down. So that is the first component. And the second component is basically the twist. So the shorter interest rate goes lower, and the longer interest rate goes higher. So if we make the graph of interest rate, okay, so this is the maturity. And so maturity. And if we think about the yield curve, then the second component is the twist. So originally, maybe, so suppose the yield curve is like this, then sometimes yield curve becomes this. So lower interest rate gets higher, and longer interest rate gets, shorter interest gets higher, and the longer interest rate gets lower, or the other way around. So that is usually the second component. Third component and following, it's really hard to interpret. Yeah. So this is the idea of principal component. So next time I discuss the mathematical algorithm for principal component. Then yeah, so that's it for today. So if you don't have questions, let's see you next week.
Thank you. Have a good night.
Thank you.